All right, hello class. We're moving right through our discussion of time dependence into our first real non-trivial result having to do with time-dependent response theory. So that's on the agenda today. We will, by the end of this lecture, understand how a thermal system responds when a time-dependent force is acted upon it, provided that force is small. So this will be a dynamical generalization of the results we've already seen in class. And to do it, we'll follow a similar sort of procedure as we did before. We will work out an exactly solvable harmonic case, a harmonic oscillator experiencing time-dependent force, to kind of illustrate how an exact calculation would look, and then generalize that in the limit that we have locally harmonic fluctuations about some maybe collective variable. Before we get there, there will be a couple points of order. We'll need to discuss a few more properties of time correlation functions. So that's up first. And after that, we'll discuss, in order to solve a harmonic system, or specifically its equation of motion, we will employ Laplace transforms, the stepbrother of the Fourier transform. And so I'll go over a few of the useful tricks that are often employed in dynamical systems using Laplace transforms. So that'll be a little bit an aside that'll happen shortly. Okay, well, let's go ahead and start. So time-dependent response. But first, some properties of time correlation functions. TCFs, if you will. Okay, so we have written down simple time correlation functions, averages of some variable A times some variable B at some distinct time. Now, those are that averaging operation means that those variables are averaged over an ensemble of initial conditions that are Boltzmann distributed. Or, if you will, propagated using a Liouville equation from an initial measure invariant under that action. Now, the equilibrium distribution, being a stationary state of those dynamics, means that for the phase space, all R positions and P momentum, the fact that that distribution on the phase space is invariant means that that time correlation function is independent of its origin. Namely, I could rewrite that time correlation function as a function of A at some T prime, B at some T double prime, if T double prime less T has the extent T. Namely, I can add and subtract T primes from whatever side I want, and as long as I do that in such a way that I look at how two variables are correlated at the same time displacement from each other, I'll get the same answer. So that comes from stationarity. The insensitivity of a time correlation function to an arbitrary origin of time. Now, a non-trivial consequence of stationarity would be to take the derivative of a time correlation function with respect to its origin. So if I ask for the time correlation function of variable a at tau and b at t plus tau, that correlation function should be invariant to the choice of tau. I could have set tau to 0. So this derivative must be equal to 0. That by itself is not all that exciting until we recognize that a is a functionally dependent variable on tau, as is b. So this derivative also equals a dot at tau bt plus tau plus a at tau b dot at tau plus t. And that must be equal to 0 from the line above, meaning that a dot at tau b at t plus tau must be equal to minus a of tau b dot of t plus tau. Or evaluating tau at 0, as I am free to do, I find a property of time correlation functions that reflect their symmetry about the origin. Specifically, if I chose b, some arbitrary variable, as a, this implies that a dot at 0, a at t must be equal to a dot of t a 0, or that has to be true for all times t. A dot a must be equal to a dot a with a minus sign. The only way for that to be true is if both are identically 0. Which tells you that correlation function of the same variable a with a at some time t later necessarily have to be even functions. Their first derivative with respect to time vanish. So a time correlation function is an even function about the origin, or an autocorrelation function. In general, we can think about time correlation functions having either even or odd symmetry. Under time reversal. Let's define observables and their time reversed counterparts with an A. So this is some function of phase space. at some time. It's a function of phase space at some time. Phase space has two components, R at that time and P at that time. So this would be the usual variable A propagating in some forward normal direction of time. I could ask for the time reversal of that operator, call it a bar, which means that I look at the time reverse of variables that are odd under time reversal, things like the momentum. If I turn the momentum around as a time derivative of the position, there's an explicit anti-symmetry in time of the momentum. Things going forward in the forward direction of time carry one momentum. They go backwards in time, they carry the opposite momentum. So I can define a time reversed observable A bar. By flipping the momentum, any momentum components of that observable around. Such that a correlation function A of 0, B at t is equal to A at 0 bar B bar of minus t. So I can move the observable B backwards in time by flipping around its momentum if it's dependent on momentum, or ask for the same quantity of positions just as they are. Now, if A and B are solely functions of position, position being an even variable in time, then A of 0, B at t, which equals A bar of 0, B bar of minus t. Must equal A. The bars don't mean anything, so that's the same as A of 0, B at t minus t. I could add t to both due to stationarity, and I would get A at t, B at 0. Which also then must be an even function in time. If I go forwards or reverse in time, correlation functions of just position are going to have 0 first derivatives about the origin. So going forward or reverse, I get the exact same answer. In fact, this is even in time for all times. A at 0, B of any time is equal to A of 0, B of minus t for any t. If, however, both functions are functions, so if if they're both function of momentum, then both will change under time reversal, and so it will be overall even in time as well. If A is a function of momentum, and B is a sole function of position, those two quantities have different time reversal symmetry dependencies. Then A at 0, B at t is equal to A bar of 0, B bar of minus t. This is also equal to A at minus t, B at 0, that's stationarity, or A bar of t, B bar of 0. If it is odd, if A is odd under time reversal, but B is even, being a function of position, I will get a minus A at minus t, B at 0, or minus A at 0, B at t, again through stationarity. So this correlation function, being a correlation function of a momentum variable and a position variable, is then odd for all time. And as we found up here, a correlation at the origin, a correlation function that is between an even variable, A, and its time derivative, an odd variable in time, has to be equal to 0 at the origin. So a correlation function that looks like R at 0, V at t must be equal to 0 at t is equal to 0 and pass through the origin with some finite slope. Okay, so those sorts of time reversal operations are useful. We can rewrite time observables and their conjugation under time reversal depending on how different observables, what parts of the phase space different observables depend on. Okay, so those are a few notes on time correlation functions. So now let's go and introduce an exactly solvable model for which we can understand its dynamical response properties. Let's call this the dynamically forced harmonic oscillator. So what I mean by that is a system for which the Hamiltonian, the object whose gradients give us an equation of motion, a la Hamilton's equations, takes the form of 1/2 mx dot squared plus 1/2 m omega squared x squared. There is the Hamiltonian of a harmonic oscillator in one dimension. Call that some reference. And add to that harmonic oscillator a force, which we know how to introduce as minus F times X, but now F varies in time. So we have a harmonic oscillator with mass m, frequency omega, a corresponding spring constant m omega squared. And we could ask, how different is the evolution of x, call it x of t, with and without this force? Specifically, we can compare trajectories traced out of that harmonic oscillator under the action of that time-dependent force and ask how different are those from the trajectories that that harmonic oscillator would have traced out in the absence of the force. To do that, we would first need to remind ourselves what the evolution of a harmonic oscillator in the absence of the force looks like. That, of course, is given by the solution of the ordinary differential equation. The acceleration is equal to the force. Note, one defines the spring constant with m omega squared precisely because in Newton's equation of motion for the position of the particle, that equation is independent of the mass of the particle. Or otherwise to say that the frequency depends on the mass in this way. Okay, so how do we solve this equation? Does anyone remember how you compute x of t given some initial conditions? Say some initial position. It's a second order ordinary differential equation, so we need two conditions. We could give it an initial position and initial velocity. So the simplest way I know to solve a differential equation of this form is using Laplace transforms. Indeed, one can solve it with Fourier analysis, just integrating exactly. That's also not so difficult in this case. However, when we add the force, really the only way to solve this equation is with Laplace transforms. So let's take a bit of an aside and remind ourselves some properties of Laplace transforms. Okay, so let's define script L acting on the function gt as the operation of the Laplace transform on the function g of t. such that the Laplace transform of g of t is equal to a function g tilde of s, where s is a Laplace variable playing the role much like a Fourier variable k or omega. The Laplace transform itself is defined as an integral transform, much like a Fourier transform. However, this is one-sided. It integrates time from 0 to infinity and convolutes our original function g of t with a decaying exponential minus s times t, where s is a strictly real variable, and thus this integral is defined strictly on the real numbers. The inverse defined as, or denoted as L to the minus 1 of g tilde of s, should give us back g of t. The Laplace transform should be an invertible operation. Its calculation, however, is a little more complicated than Fourier transform. It is given by a contour integral, factors of 2 pi I over the Laplace domain, the function, Laplace transform function g tilde of s, e to the positive s of t, or this domain L is a line integral in the imaginary or complex plane such that the real part is greater than any singularities in g tilde of s. So in the real and imaginary plane, we might have some singularities. Whoop. And we need a line such that that is true. Looks complicated and is often. However, many Laplace transforms, because it's invertible, one can compute the forward transform and thus know the inverse by construction. So some typical examples. Would be, say, g of t is equal to just a constant, in which case g tilde of s being equal to that exponential integral is just 1 by s. If g of t is equal to a delta function, g tilde of s popped through that exponential integral will be equal to minus s times where the delta function is equal to 0. Other common functions for a transform or Laplace transform might be an exponential, e to the minus gamma t, g tilde of s. The Laplace counterpart would then be two exponentials. I would just sum the arguments of those exponentials, turning this into s plus gamma. Analogously, gamma need not be a strictly real number. I could Fourier transform, or I could Laplace transform, say, the sine function, which I can write as 2 pi I, a sum of complex exponentials. And through this simple identity here, arrive at the Laplace transform of the sine function, which would be 2 pi I, and now a sum of these fractions s minus I omega minus s plus I omega, or omega, finding a common fraction, multiplying top and bottom by complex conjugate, I get omega over s squared plus omega squared. Similarly, the Laplace transform of something like cosine omega t, done exactly analogously, yielding s over omega squared plus s squared. So those are common functions. The thing that makes Laplace transforms particularly suitable for solving ordinary differential equations is the following property. If I took the Laplace transform of the differential operator acting on a function g of t, well, through my definition of the forward Laplace transform, that's an integral over time d dt g of t, quantity times minus s times t. Without knowing what that function is, so it's possible I could differentiate that function, but without knowing what that function g of t is, I could still rewrite this using an integration by parts. I would get g of t e to the minus s of t evaluated at 0 and infinity. That's a boundary term that need not be 0. Minus the derivative of e to the minus s of t gives me a plus s integral g of t e to the minus s of t. This is nothing but g tilde of s. This is evaluated at minus infinity, 0, independent of what g of t is, as long as g of t is itself regular. Evaluated at 0 gives me minus g at 0. So what we have just found is that the Laplace transform of a first order derivative gives me back of a first derivative of a function g gives me s times the Laplace transform of that function up to a boundary term, an initial condition term. Analogously, taking the Laplace transform of a second order differential can be followed through, giving me integrating by parts twice, two factors of s times the Laplace transform of the function g of t, less s times g at 0, minus g dot at 0. So that is going to be directly useful in our calculation of the harmonic oscillator, being a second order ODE. Also, it's worth noting that Laplace transforms satisfy a convolution theorem, namely that if g of t is equal to an integral over t prime c of t prime h of t less t prime, that the Laplace transform of g of t is equal to the Laplace transform of h times the Laplace transform of c. Exactly as it works in Fourier transforms. Okay, so those are some properties of Laplace transforms, some quantities forward and reverse transformed, noting these particularly useful properties of Laplace transforms of derivatives, and noting convolutions, we're in a position to apply that to the solution of a simple harmonic oscillator. So going back up here, there's our harmonic oscillator equation of motion. I'll claim that we can solve for x of t using Laplace transforms. Let's see how that works. So here's our equation of motion. Simplified, noting we can cancel out the mass on both sides. If I take the Laplace transform, I will get on the left-hand side, using the property we just noted of the Laplace transform of a differential, s squared, the Laplace transform of x of t, less s times a boundary condition in space and a boundary condition in momentum. And that will be equal to minus omega squared, the Laplace transform of x. And now I have turned an ordinary differential equation into an algebraic equation. Hence the great utility of Laplace transforms. Solving for x tilde of s by bringing the right-hand side over to the left and the constants over to the left, over to the right. I have x of 0 times s divided by s squared plus omega squared. Hey, that's a Laplace transform we just worked out a second ago. And I will also get x dot, a constant, divided by omega squared plus s squared, another Laplace transform we just worked out. So inverting this, s over s squared plus omega squared, that's going to be x naught times cosine of omega of t. All right. Plus x dot of 0. If I multiply this by omega, and divide that by omega. Omega over omega squared plus s squared was the Laplace transform of sine omega t. And thus we've just solved the harmonic oscillator equation of motion. Harmonic because it periodically changes with a frequency omega, given some initial position and some initial momentum. So this is for f is equal to 0. So this is the equation of motion solved for the position of our harmonic oscillator in the absence of the force. So let's denote this with a little subscript 0. For being without the force. With f of t, note what would have changed. I would have had x double dot is equal to minus omega squared x minus plus f of t. Laplace transforming all of this, I would have gotten exactly the same thing as I did before. But in addition, I would have the Laplace transform of that force, like so. All of this is the Laplace transform of the original dynamics of x. And here we have the difference between that evolution with and without the force, just given by, in Laplace space, a product of the Laplace transform of the force over omega squared plus s squared. So let's define this denominator as g of s in which case g of t is equal to 1 over omega sine omega t, taking the Laplace transform of that. Now note, if we inverse Laplace transform this term, that has the form of g of s times f of s, which inverted is a convolution. So inverse Laplace transforming the left-hand side, we get x of t. The first term is what we would have gotten in the absence of the force. And in addition, we now have a term that goes like a convolution of this function g with the applied force. So we have solved for the difference of the evolution of x in the presence and absence of the force. And it is equal it is linear in the force with a kernel that it's convoluted with this g that is denoted g because it is called the Green's function. Or, in the language we've been using statically, the response function. It tells us about the response of the trajectory to this additional linear perturbation. This was exact, as we might have anticipated for our harmonic oscillator, in that linear response is exact for something that exhibits Gaussian statistics. It relates the equation of motion in this harmonic potential in the absence of the force. If we turned on the force at some time 0, then we should follow the original trajectory up to that time, and only after that time follow the new trajectory, the perturbed trajectory. We could define a chi of t as the step function theta of t times g of t, where that step function is 0 for arguments less than 0 and 1 for arguments greater than 0. In which case we can then replace chi. My x's and chi's look pretty similar. Sorry about that. And now have a response that obeys causality. If we only turn on the force at 0, that g of function shouldn't offer any change to the equation of motion until that time. Moreover, we can relate chi, the response function, to thermal fluctuations, to a correlation function in the absence of the force. Just as we have before. Specifically, if I looked at the time correlation function of x at 0, x at t, which I can compute through knowing the solution x of t in the absence of the force. That is x of 0 squared cosine omega t plus x dot x of 0 over omega sine omega t. Taking an average of the left-hand side gives me the correlation function in the absence of the force, which is equal to, again, these averages are averages over initial conditions. So I average x squared over a set of initial conditions. That's just a thermal average, which gives me 1 over beta omega squared from equipartition times cos omega t. Then I average x dot at 0, x at 0 over omega sine omega t. But now that is a thermodynamic average of an even and odd function of time, which means that that average is identically 0. And now look at what we've just found. If I take the time derivative of x of 0, x of t, averaged in the absence of that time-dependent force, I get minus 1 over beta omega t sine omega t. Sorry, no squared there. Which is equal to up to a factor of 1 over beta and a minus sign g of t, that Green's function. So the Green's function, or putting everything together, the response function that tells me how my trajectory changes can be given by minus beta, the theta function, which invokes causality, and a time derivative of a time correlation function. So again, we have found that response is related to fluctuations or correlations in this case, in the absence of the force. This explicit expression is what is actually most commonly referred to as the fluctuation dissipation relationship, or fluctuation dissipation theorem. As we've just demonstrated, it is exact for a harmonic oscillator, and now you might expect to be approximately true in the limit that the perturbation is small more generally. And that's what we can work out in the remaining time of class. Okay, so let's see that. Okay, so more generally, we can consider an arbitrarily complex system obeying the Hamiltonian H, acting on our phase space, that is decomposable into a reference acting on that space minus a time-dependent force that acts on some observable A in a linear way. So here is what encodes our reference. And here is our linear perturbation. In the presence of f of t, that Hamiltonian is time dependent, so the system, the evolution of the system itself, is not stationary. So any averages taken at finite f are really non-equilibrium averages. So we need to delineate equilibrium averages from their non-equilibrium counterpart. Let's do that as we have introduced previously with a bar. So let A bar of t be an average over independent realizations of this perturbation. So when F is finite, we have this non-stationary distribution, non-stationary dynamics. However, when F is 0, we have a well-defined Hamiltonian and thus a well-defined equilibrium ensemble from which we can draw initial conditions. And for which we can denote averages over those equilibrium ensembles, bracket A. So let's now ask the question, what happens to the evolution of this observable A as a function of time subsequent to turning on this time-dependent force, where it will generate a non-stationarity, a explicit time dependence? Well, one way to go about answering that question would be to consider the average A of t as A being a functional of time, a functional of the phase space evolution of the system. And imagine that if F is small, I can treat through a functional expansion that evolution of A. Namely, to 0th order, I would have the evolution I would expect in the absence of the force. And to 1st order, I would have a time integral of the functional derivative of A of t with respect to F of t prime evaluated in the absence of the force times F of t prime, and this would be up to F squared, which if F is small is reasonable. Now let's define chi of t and t prime as that functional derivative, defining the response function, how A responds to F in the absence of the force. And note that if I start in an equilibrium, if the reference is an equilibrium reference, that chi of t comma t prime is equal to chi of t minus t prime due to the stationarity of equilibrium time correlation functions. And it must be that chi of 0 is 0 for t less than 0. Namely, causality must ensure that A of t bar does not differ from A bar not before the force is turned on. Imagining that the force is turned on at the origin of time, t equals 0. Something to note here is that chi of t is independent of the force. It's computed in the absence of any force in this reference ensemble, in which case the system doesn't know what happens under the evolution of finite F. Indeed, in general, we can compute response functions by imagining arbitrary kinds of perturbations because of this invariance to the specific form of the perturbation. A specifically convenient thought experiment to try to understand chi, the response function, is to imagine that we consider a step response. Namely, imagine equilibrating the system under f of t is equal to a constant. So turning f of t, so slightly different from what we imagine, saying f of t is equal to f bar from t is minus infinity to 0, and at t is equal to 0, turning f off. Namely, that f of t is equal to f bar for t less than 0 and 0 for t greater than 0, or that f of t is equal to f bar 1 minus theta of t. That is a convenient thing to do because for times up to right before the perturbation gets turned on, the probability of a configuration in the full phase space is Boltzmann distributed with that constant force. Namely, I know what the distribution of microstates are. They're distributed in a Boltzmann form. I also know at infinite times, assuming the system relaxes, that the system will equilibrate under a new Boltzmann distribution given by the Boltzmann factor in the absence of a force. So I know the endpoints given this step perturbation. Therefore, I can ask questions about what happens at intermediate times, say t greater than 0. Well, the average of A of t is going to be deterministically given by the set of initial conditions generated when I turn the perturbation on, which are Boltzmann distributed, times the time-dependent evolution of A, but the time evolution is given by the action of just the reference Hamiltonian, so the equations of motion in the absence of this force. Now, the statistics in the presence and absence of the force, the two partition functions normalizing these distributions, are related in the normal way. We've seen this many times. Q of f can be written as Q naught e to the beta f bar a averaged in Q naught. Now, that's our usual generating function. For small f, I can relate the probability of a configuration in the presence of f to that in its absence. That is given by taking, this is not a quantum mechanical system. I can separate those exponentials. QF is equal to Q naught over this average. For small f, this is P naught always. For small f, I can Taylor expand those exponentials. There are two of them. The numerator will give me 1 plus beta f bar a to first order. The second one in the denominator gives me 1 over 1 plus beta f bar a under the averaging operation. 1 over 1 plus a small number is 1 minus a small number. And so I find that the average, the distribution of initial conditions in the presence of the force is equal to a distribution of initial conditions in the absence by a factor of these cross terms, 1 plus beta f bar a times 1 minus f bar average a. Plugging that in, a of t bar, which is given by a phase space average of this probability in the presence of the force. I have P naught. I have an A of t. And now I have to first order in F 1 minus beta f t average A in the absence of the force, 1 plus beta f bar A. That is then all averaged under the absence of the force. I will get a first order term, which is just average of A of t in the absence of the force. I will get a plus beta f bar so let's take this term. That's average of A at 0, those initial conditions, average of A of t. This term with this term are averaged separately. I get minus beta f bar, average of A of t. Putting that together and noting that an equilibrium average at one time is just a thermal average. I have that the time dependence on average of A of t in the limit that beta, that f is small, is given by beta linearly scaling with f and a time correlation function of the fluctuations at A at time 0 and A at time t averaged in the absence of the force. Equating this with our initial expansion here, our functional expansion for A of t, we find that A bar of t is equal to average of A plus f bar integral chi of t minus t prime 1 minus theta. That's the perturbation. Just plug it in here. What force we're talking about, F bar 1 minus theta. Now, if I take the time derivative, saying that this is equal to what we found up here, so the average of A's in the absence of the force cancel. I could take the time derivative of beta F bar correlation function of A in the absence of the force. That's equal to the time derivative of this side, which is F bar integral chi 1 minus theta. The F bars cancel. I can now, this is the derivative of t, which acts only on chi, giving me, bringing that inside the integral over t prime. I get d derivative of chi t minus t prime 1 minus theta of t prime. Now that derivative, because chi is a function of t less than t prime, I could act on chi with respect to t, or through a chain rule t prime, giving me a minus sign, as that's how its arguments change. I could further do an integration by parts, assuming the boundary term is 0, which it is by construction, and act rather than on chi, on the step function. The time derivative of the step function is a delta function. That's a delta function at the origin, t prime equals 0, which then kills that integral, giving me chi of t up to a minus sign. So what we have just found is that chi of t is equal to minus beta, the time derivative of the time correlation functions of A in the absence of the force up to a theta function that invokes causality. So this is a neat enough result. Ooh, that's way too small. That's a neat enough result. Let's highlight it here. So this is a statement of the fluctuation dissipation theorem, as we just saw before. It tells you something incredibly deep and interesting. It says that the way in which a system relaxes, mind you, that's what we're doing here. We started with a constant force of scale F bar. We turned it on, we kept it on at minus infinity in time and turned it off at time 0. What we've just uncovered is the way that A responds to that, the way it would relax, is exactly how it fluctuates in the absence of that force. So if I were to just observe a spontaneous fluctuation of A that took it up to some rare value, and then followed that subsequent relaxation from the thermally excited state, that the way the system relaxes from that state is exactly how it relaxes if it is actually perturbed in some small way. So encoded in the dynamical fluctuations, and specifically the time correlations of an observable, is how that observable relaxes under a perturbation. Now, this has a long history. Note that there was some real subtleties in actually going through this derivation in a way that was not trivial like it was statically. Namely, we had to set this calculation up where we knew how we propagated the system under time. So we were acting this observable with a Liouvillean that was a reference, and we rewrote that phase space average as an ensemble average also in that reference. So it is, we required understanding both the structure of the dynamical evolution of a complex system in addition to how that system is distributed statically. That required much more advanced mathematics than to first rigorously prove when it was first proved. Mathematics that didn't exist when Onsager first intuited this result. So Onsager, through what is known as his regression hypothesis, suggested that this is how macroscopic systems relax through small perturbations, which they do as they would have done just from relaxing away from spontaneously established departures from equilibrium. He postulated this in 1931, I think, and it took like 20 years for people to actually prove it. So Kelm and Welton proved this relationship that I've just shown you in 1951, and they won a Nobel Prize for that. All right, so this establishes a connection between fluctuations and response. It gives us a handle by which we can start thinking about the response of dynamically evolving systems. We have a couple things to do next. We can first apply this to some cases we care about. We'll do that shortly. We can also generalize it to the case of not classical Hamiltonian mechanics, but quantum mechanical evolution. And then, much like we did before, we can then try to construct models by which we can derive these correlation functions and thus have a closed theory. Okay, well, that's all I've got. Thank you for sticking around, and I look forward to seeing you all in the live sessions. Do everyone start thinking about your projects. If possible, you might begin reaching out to me to set up times to discuss potential projects to work on. In principle, I'd like you all to have a firm idea of what you'll be working on by mid-March or so. All right, well, everyone take care, and I'll look forward to seeing you in the small groups.